So good morning, I am Nikos. I'm a data scientist at GRNET. GRNET is the National Infrastructure for Research and Technology in Greece. We operate the Greek supercomputer ARIS, and we are working on Daedalus. Most probably it will be ready on 2026. And we are the NCC of Greece, the corresponding entity for EuroCC in Greece, and we have a very strong collaboration with the Cyprus Institute in HPC, AI, and other projects. My part is of the presentation is a very basic introduction to RAG, to retrieval augmented generation. And actually, it consists of three parts. I will start with transformers. We will see some basic function calls of the transformers library, which is perhaps the most important library for LLMs. Then we will move to embeddings, how we encode words and sentences into vector, into a numerical representation. And then we will combine the first two parts to explain RAG. We will use context in the user's queries, and we will get the responses, as Chris said previously, grounded to this context. I would prefer if we have an interactive section. This is a hands-on section, actually, so you can interrupt me, you can ask me questions, or have brief discussions after each step. I have shared in the link, in the Zoom chat, the link of the notebook. The only thing you need is a Google account. If you have Gmail, you can directly run the notebook. And also, throughout the notebook, I have an HPC in square brackets flag, where you can run some more commands, and the same code, however, the same code, you can run it on an HPC environment, on a cluster. So we will present it on Colab, but the same can run it on a cluster. The first thing we need to do is we will need an environmental variable, the hidden face token. This is necessary in order to authenticate and download models. And you can generate one even now if you don't have via this URL, hidingface.co/settings/tokens. You will only need the read permissions. No need for write permissions, and actually it is better to avoid any misuse of the tokens. Okay, so I will wait a bit here, and I will ask if you have a token or if you have difficulties creating one. Can you please give me a feedback in order to see if we are aligned, either from the Zoom or from the class? Let me ask it differently. Is anyone that already has a token, a hidden face token? No. The key carbon apparently is not working. Okay.
You need to.
Basically, you can start with a Colab now for this session. Can you please write me on the chat if you can view the Colab notebook and if you have a hidden face token? Collab works fine. Okay, thank you. Nice. Thank you. I have a token. Great. Okay, nice. Thank you very much for the feedback. As I said, I'm asking because I want to make it a hands-on lab. I believe it is better for your understanding. So that's why. Okay, so I will continue. We will, through this notebook, you can run any model of any hiding phase model, given that you have enough compute power. So for running them on Collab, Collab gives us 16 gigabytes of GPU RAM. We will run some small models. I have indicatively here two well-known models, Mistral and Llama, but you can also run any other model. Now, I will open the link of Mistral because we will need to authenticate for the model now in order to get access. Some models are called gated on hiding phase, and they need permissions. So here, if I open the link of Mistral 7 billion, you can view that it displays gated model. You have been granted access to this model. If you don't have access, you can, somewhere here, you should see some terms and then introductory text, and you can click request for access. It is a blue button. I don't remember the exact text, but it is something like that. And you can check if you indeed have access in gated repos. In hiding phase, you can go in your settings, gated repositories, and you can view which models you have access. If everything is running fine, you will view there Mistral 7 billion dash instruct v0.3. This is, again, very important, and we need to finish this before proceeding, because if we don't have access to the model, we will have troubles downloading it. I also have Llama. Llama, the last few months, has some issues. Many users have faced some issues downloading the model. That's why I start with Mistral. If you go to community here, you can view some request for access problems. And in any case, as I said, you can go to models on hiding phase and select any model that you want to use. The only, of course, we are talking about text generation and preferably instruct models. So, for instance, you can sort them by most downloads. Here you can get QN 7 billion. You copy the handle of the model and you just paste it in the next cell here if you wish to use another model. Okay, this is about hiding phase. Now, I have to ask again if you have acquired access to the Mistral model. If you see here in your gated models, if you see gated repositories, if you see Mistral 7 billion, please write me on chat or open your microphone, whatever you like. The question is if you have access to Mistral. The link is at the beginning of the node here. And the link for the gated repos is here. If the direction is not working, you can double click on the markdown and you can copy the link. Okay, I see some people have already installed. Thank you, great. If someone has troubles getting access, please let me know to resolve it as soon as possible, because we will not proceed otherwise. Okay, nice. Okay, I will continue, and if you want, you can ask. Now, in order, it is very important to say that the tokens should always be environmental variables. We never save them on files because they are very important variables. Sorry, the repo was private for the action. So in order to make HF token experiment environmental on HPC, you will run these commands. If you see the HPC flag, you can ignore it for now, but you can run it on a cluster. These are the dependencies. For Google Colab, everything is pre-installed, actually, so the only thing we need is bits and bytes. Bits and bytes is a library for the quantization of the models here. It reduces the size of the model because we only have 16 gigabytes of RAM, so we will use less precision in order to have to need fewer GPU RAM and also to have faster models. If you have bigger compute, you can ignore bits and bytes. I have Mistral, but Llama is pending. Yes, Llama has some issues. As I said previously, if you go to the community tab, many people have issues getting access. So that's why I will start with Mistral today, but you can also download any other model, usually up to 7 billion parameters. If you go more, everything will crash. I mean, for this compute power. Okay, so let's start by installing bits and bytes. I have already installed this. Please run this cell, the first cell actually. Pip install, upgrade, bits and bytes. It takes around 1 minute, something like that. And you will get the installation of the bits and bytes. Yes, these are HPC commands for the allocation of the resources. As I said, for today, you can ignore them and you can run them perhaps later. Now, having installed bits and bytes, you can proceed with the imports. We will use transformers. Transformers is the library for running and fine-tuning and training large language models. It is the golden standard now. And we also import OS, torch, time, and regular expressions. And here, on this cell, you will set your Hugging Face token as an environmental variable. If you run this cell, you will be prompted in a new input text box to give the model, and it will be stored hiddenly in your own environment. So here you run this and you set the HF token. And finally, as another preparation step, we need to set, this is not necessary, HF home is the directory for downloading the models, where the models will be stored locally. Locally, we say on Colab. And I set this specific path in order to have easy access to my model. You could skip this and you could use the default. Then I said I give here the name of the model. You can get this from here. If you if you click the double square button, you will copy the model and you simply paste it here. So here we set the name of the model. Yours on the cluster, I don't know if this is for me. Let's discuss this in a while. Okay, yes. So my model, I set my model, and we need, in order to continue, we need to download two things. The first is the tokenizer, and the second is the model itself. If you notice, here I imported from transformers auto model for casual LM and auto tokenizer. The tokenizer will transform the inputs, which is text, which is a string, into PyTorch tensors. And we need this transformation in order for the model to be able to, let's say, understand the text. And then is the actual model that we need to, that we will use. Here, it will take some time. If you click these two cells, the second cell will take more time because it will download the model. It is, if I remember, around 7 gigabytes. Here, you can view the weights of the model, the safe tensors. It is more, it is almost 5 plus 4.5. It is around the total, around, it has the consolidated tensors, 14 gigabytes. And that's why it will not fit on the RAM, because we have some overheads. Colab has 16 gigabytes of RAM, so this will be very difficult to fit. And that's why we use the bits and bytes library, and we will load everything, the model in 4 bits, in fewer accuracy, in less accuracy. Do you know what to specify? Okay, I will wait here a bit for you to download the model, and please, it will take like 3 or 4 or 5 minutes. So if somebody has already downloaded the model, please write on the chat in order to know what is happening. Now I will try to answer the question. Do you know what to specify for QoS? QoS, it depends on the cluster, actually. Do I have QoS in my commands? It is the cluster partition. I don't know if I have QoS here. Let me check. QoS default, yes. Okay, this is a correct point. Actually, this implementation is for Meluxina. Meluxina is one of the EuroHPC joint undertaking supercomputers, one of the 8 biggest machines in Europe. And on Meluxina, you have various clusters, various partitions on the cluster, and here I define the default. For Cyclone, I don't remember if it has a QoS. Perhaps you can ignore this and try to run it without this command. No need to specify, it is already answered. So now I see, Chris, your response. So we say the same. Okay. Okay, so I am waiting. Yes. Can you tell me if you can view here some green bars, increasing green bars corresponding to the downloading of the model? Probably you have already downloaded the tokenizer, and you are now downloading the model. Please write on chat to be aligned. It's getting okay. Green bars, nice. Thank you for the feedback. Nice. But took 12 minutes, eh? Now this depends on the speed of Colab of the internet on Google Colab. Sometimes it is faster, sometimes it is not so fast. Okay, if somebody wants to ask me something till now, please open your microphone and tell me. Otherwise, I can continue with some more commands while the model is being downloaded. That's okay. So here, this is not always necessary, but some models need to specifically specify the pad token to be equal with the EOS token. These are technical for transformers library and for the transformers architecture in general. EOS token is the end of string token, and the pad token is the tokens that we put for the unknown, for the missing words. For instance, the transformers, in order to function in classical machine learning in a database, every instance of the dataset has the same length, has the same number of features. In natural language, we don't have this same number of features, so we have to convert them to the same number of features. And that's why we need the pad token. The missing words, we use a specific token for the missing words. And some models need to specify that the pad token is the same with the end of string token. So, okay, I mean, you can just run this command without more in-depth investigation. Then we will need a streamer. A streamer will help the model provide its response in real time because LLMs are heavy models, and perhaps it will take like half a minute or 1 minute to get the response. By using a streamer, you can get the response in real time while the model is also simultaneously processing your request, and it is very helpful for chatbots and assistants, etc. And here in this cell, I will define the messages. What I am sending to the LLM, the messages are actually a list of dictionaries from a Python perspective. You can see here the square bracket for the list and the curly bracket for the dictionary. And we start with some, usually we start with some system instructions. We give some, this is perhaps the most important message we send to the model. This is the role of the model, what it is supposed to do. Here, I have a very generic system instructions. You are a helpful assistant. However, in many cases, especially in RAG, we need more, we need to work on the system instructions to specify a role. For instance, if you create an LLM for legal processing of legal documents, then you can tell the model, you are an experienced lawyer on commercial law, for instance. Your role is, your task is to do this and that. The first is this. for RAG. The second is it is a very good idea when we are using RAG to explicitly tell the model from the very beginning, from the system instructions, that it should adhere to the context that we will give to the model. I will make this more clear a bit later, but it is very important for us to apart from providing the context, to use some prompt engineering in order to tell the model that it should be focused on the context and not answer on its own judgment, whatever, its own knowledge. Okay, so we define the first element of the list, which is the system instructions, and then we append a second dictionary to a list. The list is my messages, dot append, and here we say role user. Previously we had role system, now we have role user. We have one more, which is the response of the LLM, role assistant. So here role user, content, my prompt. And my prompt here, I will stress a bit the model. I am asking it, explain linear regression using label. Use D as the symbol for the dependent variable, and I, capital I, as the symbol for the independent variable. D is for dependent and I for is dependent, because usually the models are using Y and X for regression in the regression equation, and we will see if it is working. We have some questions. I got this error in let me check this. I have a message here. Yes, I don't know. Does anybody else has an HTTP 401 here in the tokenizer? No. No. I'm afraid that I don't know this. Let me ask it differently. Can you? I will ask again if you can tell me if you have tokenizer and model. Some more people have had two answers previously. If the downloading of the tokenizer and the model is finished. Yes. Okay, so it is working now. Yes, okay. Okay, okay, that's. I will proceed and we can check it out also later. So here we have our messages. Okay, actually we have a list of two dictionaries, the system instructions and the first prompt to the LLM. It's downloading. Okay, it will be soon downloaded, hopefully. Now, afterwards, I remind you the tokenizer is an object. It is defined here. It is an auto tokenizer instance, an instance of this class. So we have the tokenizer. This object has a method named apply chat templates. Chat template. Here we give as an input our messages, and it returns tensors. So if you run this cell, you will view in the print here that the type of the inputs now it is a PyTorch tensor. Previously it was a list of dictionaries of strings. Okay, now it is PyTorch tensors. This is very important. That's why transformers is very useful. Otherwise, I mean, it would be very hard, but you will have to do it manually. Still downloading it. Approximately what percentage it is? It is at least the half downloaded or 1%. Andreas or Panagiotis? Just finished. Okay. Nice. Yes, it takes some time because it's very important to understand that now we have the model finished. Okay. Locally in quotes on Colab, but I mean, these are not API calls. You run the model, you can run this on your laptop without internet in order to make this clear. Okay. And then I continue to moving the inputs to the GPU. And I say because we can run the model on the CPU as well. If you don't have a GPU, you can run it on a CPU. Of course, it is much more, it will be much more slow, 30%. Okay. We wait. Okay. Okay, so here I say inputs equals input if I have a GPU, which is this well-known PyTorch command. Inputs equals inputs dot to CUDA. And I do the same for attention mask, and I print an informative message. And finally, here is the magic, where we actually call our model. I provide a maximum tokens variable. Okay, sometimes the models are very verbative and they provide very big response, so we need to stop the response. And I give the inputs, which is the PyTorch tensor, the streamer, which is the streamer object, the path token ID. I explicitly telling that it is equal to the tokenizers, the specific tokenizer I downloaded, end of string token ID, the attention mask, and the max new tokens. And I get the response. Now, if you notice here, you see they are not so much processed, the responses of the transformers library, because you can view also the system messages and the user's instructions. You see here, inst, you are a helpful assistant, explain linear regression using LaTeX, use the blah, blah, blah. And then /inst, and here is starting the response of the model. Linear regression is a statistical method, blah, blah. This is the response of the model. Most probably you can view it in real time. Now, so actually, now, this is the first thing that we have in the response of the model, some text that we want to remove. The system instructions. I want to get a clean response. This is one thing. The second thing is that this method here returns outputs. Outputs, if you see here, is a PyTorch tensor again. We give tensor, we get tensor. So we need to convert the outputs to decode them to back to text. So we call again the tokenizer dot decode now outputs of 0. For some reason, they are saved in the first element of this matrix. Okay, and I also use these variables, skip special tokens and clean up tokenization spaces in order to clean the response. And finally, here I print the response. Next. Okay, I can see that, yes, oh no, it is correct. yes, it removed the inst, etc., but it still has the instructions. And I need one more step. First of all, this is a class string now. It is string. I gave tensor to the model. I mean, I am telling this because even if the model is streaming, what I see in my screen is not a string. Okay, it is only converted string on the fly. The response is still tensor, a Python tensor. So here I have the generated text, which is a string, but I need to clean the string in order to remove my initial prompt. So I and the system messages. So I do this splitting here. I get the generated text dot split with a splitter my prompt. I get the second part from 1 to something, from 1, I don't remember why, probably it has a white space, something like that. And here I get a clean response. Now, this is for Mistral specifically. For other models, for Llama, for instance, perhaps we will need some regular expressions in order to clean the response. I have here a regular expression for the Llama as well. Let's have a look also in the model's response. We can view that the response is the linear regression equation, one. The linear regression equation is given by D, as I asked the model, equals beta plus beta 0 plus beta 1 times I plus epsilon. So it understood what I asked the model. This is very good. Other models cannot understand, so small models, I mean, cannot understand this. And of course, it is not guaranteed that it will always understand or it will always respond the same answer. And here is in plain text format. Okay, this is the first method of calling a model via streaming. Here I also measure the time, if you notice. Okay, I have T1 before the model and T2 after. So I also print the time here. And the time was 0.73 minutes. I can also call the model without streaming. For instance, LLMs is not only for a chatbot, it is also for text processing. Perhaps I have a big collection of text and I want to summarize all in a for loop, for instance. There I don't need streaming, I just want the response. So I can call the model without the streamer. It is actually the same as previously. Outputs equals model.generate. You see here the same. Outputs equal model.generate. But I skip the streamer. I remove this command and I have the simple response. I count again the time and it is much less. This is not always true. It depends on many things, on your system, on the operating system, etc. But sometimes it is helpful to just call the model and get the response. And finally, for the first part, for the transformers library, we have the pipeline object, which is a higher level abstraction of the model and of calling the basic model method. Where here we just we create a pipeline object. We still need a tokenizer, but we give the model the tokenizer and the device map equals auto. This is if we have many GPUs. and I get outputs equals pipe, my messages, match new tokens, etc., and I get similarly the response. Okay, I think we will continue. We have two more parts. We have embeddings and RAG. This part was for calling the transformers library. And I will wait a bit, and I will ask if you have managed to download the model, if you run the first commands, or if you have any questions, etc. Chris, in the class, is everything okay? All good, nice. Okay, so I will continue with embeddings. What is embeddings? Now, embeddings is, as you know, computers can only understand, can only process numbers, and they cannot process, I mean, in the sense of numerical computation, they cannot, and training models, they cannot process strings. So we need to somehow convert our strings into a numerical representation. And now the most prevalent, basically, most probably the only way of doing this is the embeddings. Embedding is a big vector of like some hundreds of floating point numbers corresponding to the text, to each one of the words of our document. The idea is that we create embeddings such that words appearing together frequently on many contexts, on many texts, should have similar embeddings, correlated embeddings. This is the first idea, and we used to apply an optimization algorithm like word2vec, skip, gram, etc., to create embeddings. Now with transformers, with the transformers deep learning model, one of the layers of the deep learning model of the transformers is the embedding layer, and we can directly get the embeddings from there and use them for our works. So we will use this type of embeddings, and particularly another library from Hugging Face named sentence transformers, which is a particular library for embeddings. And more specifically, we will use this model. If you go on Hugging Face and view this model, it has like 89 million downloads last month. Okay, so it is a very well-known model, and I have used this model many times, and it is working very good. Okay, so I again import some libraries. Here we will need pandas and numpy also, and scikit-learn, because we will visualize some of the results of the embeddings. And if I click on this button, I will download the embeddings model. this will take some more time, fewer than previously, because if you go on files here, it is like you see kilobytes, the safe tensors are 90 megabytes, etc. So this should be much more faster. So you download the model, you will see again some green bars here, etc. And here I have a method for visualizing the correlations of the embeddings. We will see this in a while. Now, let's have some initial testing of the embeddings model. I create a list of 4 irrelevant amongst them words, like reciprocal, obfuscate, hyperbolic, and tensor. I understand that they are not so semantically related. This word hyperbolic is irrelevant to obfuscate, for instance. Okay, and I encode, I use the embeddings model. The embeddings model, again, is an object of type sentence transformer, as we said previously, and I encode the entire list. Here I can give either a word or a list of words or a sentence or a list of sentences. Embeddings work for words, but also for sentences. And the embeddings model can accept list of words directly. And you get correspondingly a list of word embeddings. And having the list of the word embeddings, I compute the cosine similarity of these word embeddings. The cosine similarity is a metric measuring the similarity of 2 vectors. It is very similar to the Pearson correlation. It is a bit different, the mathematical formulation, but it can capture well the correlations of the similarities of the embedding. So it is widely used in embeddings. And I just print then the cosine similarity. It is this matrix here. And I visualize, as I said previously, the similarities. So to make this clear, actually I have a matrix with all of the words I gave to the model, which is reciprocal, obfuscate, hyperbolic, tensor, and all the pairwise cosine similarities. Okay, the main diagonal, here in the method, I make it 0 because it would be 1 and it would destroy the visualizations. Everything else would be smaller because the correlation of one word and itself, it is 1. So here actually I put a fake 0, and we can view that the highest similarity is around 0.2 here, reciprocal with hyperbolic. Now, the values are usually from 0 to 1. We would expect perhaps something even lower than 0.2, 20%. However, because of the training algorithm of the transformers, some association of all the words exist. So that's why we have this correlation. We will view in a while for the related words. Can I get the link to the code? Yes, I will share it in the chat again. Okay, so for unrelated words, I have small correlations that is expected. And then we have related words, book, publication, and article. I run the same code. And I can view that the similarities are much higher, 0.4, 0.5, etc. So this is a first numerical indicator that the embeddings are working well, because for irrelevant words we have low similarity, and for relevant higher similarity. Now, here I will tell this very briefly. I am doing some numerical calculation. I compute the mean value of the embeddings, the standard deviation, and the norm of my embeddings. And I can view that the mean values are around 0.39, standard deviation 0.05, and norm 1. This is expected, they are normalized. And then I compute 3 random vectors with the same statistical characteristics as my embeddings, the same statistical characteristics, the same mean, the same standard deviation, the same norm. I check the response, and indeed they are approximately, of course, they are. And I compute the cosine similarity of these random vectors. And I can view that the correlations here are almost 0, 0.1 at some point, etc. Why this is happening? Because it is very hard in a high dimensional space. Here we have embeddings of 384 dimensions. It is very hard to see, to randomly pick 2 vectors and to be correlated. Basically, we can say roughly that all the vectors are vertical, are perpendicular in a very high dimension space, all random vectors. Not all. You can do it also with Python test. This is an interesting part. And then we do some funny computations here. Here I compute the similarity of the embedding of car, of the word car, and then I compute the embedding of vehicle. I add the embedding of motorcycle, and I subtract the embedding of bike, and I compute the cosine similarities of these 2 vectors. And I can view that it is very high, it is 70%, which is conceptually expected. We would expect that approximately the car is a vehicle plus a motorcycle minus bike. Okay, and same for Greece. Is Greece equals to Athens plus Italy minus Rome. Again, 68% similarity. So we can understand that embeddings well. And finally, I have I define here a list of some sentences. The first 3 are interrelated sentences. The data is pre-processed to remove noise and outliers. Noise and outliers are eliminated during data pre-processing, etc. And the second group, again, is relevant, but the 2 groups are not related almost at all. And I compute again, embeddings model dot encode my sentences. I compute I encode these sentences now to embeddings, and I compute the similarities. I plot them, and I compute at the top left part of the figure the first 3 sentences with pairwisely again have around 0.8 similarity. And similarly for the bottom right, not so high, but around 0.5, 0.4, etc. And the top right now and bottom left are 0. So, I mean, it somehow clustered the sentences. It understood that we have a cluster at the top left and at the bottom right. Okay, here we finish the second part, and we have one more for the retrieval augmented generation. I will again wait a bit, and if you have any questions, you can open your microphone or write in the chat, etc. Okay, so having explained the transformers and the embeddings, we can now proceed with RAG. RAG actually combines an LLM and the embeddings. Okay, we import again the same libraries. No need to run them again. I have constructed the notebook such that each part can run independently, but now we already have the transformers model. It is the same as previously. And we need a text for retrieval. Here, I am giving the description of the notebook, actually, the first cell at the beginning, saying that this notebook demonstrates the use of large language models for generating text, blah, blah, blah. You can provide there any text of your own, any text that you want to process or to discuss with. Okay, so you can change this variable here. It is a very big string. You can change the text or you can use this. So this is my context. I want to discuss with my context. Now it is only 10 lines of text, but the same general idea, not, as I said, I will present a simplified version of RAG. Marius will present a more advanced library. But the general idea is the same if you have a small paragraph or if you have a very big text. Actually, we will not use RAG for such a small text because we can give it directly as a prompt or in the system instructions. So this is a toy example in order to demonstrate the basic ideas of retrieval augmented generation. So I store this string into my text, and then I split my text with a new line as separator. In libraries, in the various libraries, we have more advanced splitters, not only per new line, we can define more advanced separators like where a chapter of a text changes, or we can handle bullet points, tables, etc. It is much more harder to work with real-world documents. However, in any case, we will need to split our text. We split our text here simply with new line, and I get my sentences. And my sentences is a list of strings, actually. I remove the tailing white spaces and the new lines, and I give this list, my sentences, to the embeddings model. Embeddings model dot encode parenthesis my sentence. And I print the shape, and I also save it in a TXT file. Just TXT is not very efficient, of course, for embeddings, but we have vector databases to store embeddings. But here we can view, this is only for demonstration, we can view if it works. We can view the first line is the embedding of the first sentence. So this is a list of 384 numbers, each line. And then the user is asking, what is this notebook about? Okay, if you ask a large language model, what is this notebook about? Most probably it will answer something irrelevant, or it will answer, what do you mean? Which notebook? I don't have any notebook. So here we will try to see if by using RAG, the model will be capable of answering this question. In order to do this, we need to encode the user's question as well. We encoded previously the sentences, and now we encode the user question. So we have the my question variable, which is what is this notebook about, embeddings model.encode my question, and I get my question embedding. If you print my question embedding, you will view again this NumPy array of numbers. Now, so we have the embeddings of the context and the embedding of the question. And now we have only 10 sentences. If I have 1 million sentences, I would need to select to pick the most relevant to my context. In order to do this, I compute the cosine similarity of my question embedding and my embeddings, all the embeddings. And I sort them by argument. I mean, compute the indices that sort the similarities. And I can see that the most related embedding is the third. We start from 0, then the 8th, etc. And here I get the sorted sentences, which is my sentences of I for I in sorted indices, and I print these sentences and the similarity to the question. So the user asked, what is this notebook about? And the more relevant chunks of my context were the notebook then illustrates how to generate text. The notebook also demonstrates. Okay, so I understand that it worked. Not very big similarity, but 47 is okay for context. And I have the sorted sentences. Now, as I said, perhaps I would have like 1 million sentences. So I should select the top relevant. And here I state number of key sentences equals 3. I just select 3 sentences. This could be 30 or whatever you like. I give the system instructions. I construct my messages. And in my prompt, I say the model now. Use the following sentences. I append the most relevant sentences up to number of key sentences, only 3. And then I say in the model, answer the question, and here I put the user question. So if you see the augmented prompt, you will see, use the following sentences. The notebook then illustrates blah, 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 blah. And then answer the question, what is this notebook about? And this is hidden. We give this as a hidden text in the model, the context along with the user's question. Actually, the first part, to retrieve the retrieval part, to retrieve the most relevant questions, is some sort of a search engine. So actually, RAG combines a search engine with an LLM. And finally, I will run the model. I download again the model. We already have it. No need to run this. And I will use the pipeline object for simplicity. And I wait for the answer. What is this notebook about? And this is the final answer. This notebook is about demonstrating and illustrating text generation using a model, both in streaming, blah, blah, blah. I clean the response here. And non-streaming modes. It also explains the concept of frag. Okay, so we can see that by providing context to our model, it is capable of answering our questions. Somewhere here, my part is finished. I think I am on time, but perhaps we can have some questions if you like.
Can you hear us?
Yes, yes, now I hear.
Thank you. Can you try, we have one question here.
Hello, can you hear me? Yeah.
Yes,
Nico?
yes, yes, I hear.
Yes. Okay, good. Well, my question would be, instead of using the first three sentences that are more similar to, well, to respond the question, is it possible to use it based on the similarity rate that we get?
Yes, yes, actually we use the similarity rate. Here I select the first three from the sorted sentences. And the sorted sentences is my sentences of I for I in sorted indices. And the sorted indices is the arc sort of the similarities.
Okay, but in that case, if there are no information in the model, how can the model know that there are no information so that it can respond that I have no information about your question?
Yes, this is a very good point. Actually, we need to construct a more a better prompt. Usually we do it here. Answer the here I say the model, use the following sentences, blah blah blah, and then answer the question. I could provide a better prompt to the model, like if the context is irrelevant to the question, please provide I do not know. Please say I do not know. One idea is this. Another idea is that I can say I can compute the similarities, and if the similarities is like less than 10%, I can skip. I can bypass the calling of the model, and I can just reply predefined text. Your question is irrelevant to my context. Please try again, or I mean, whatever. I don't know if I answered.
No, thank you.
We have one
I
question.
think
in
there
the
is
chat.
also one in the chat.
Yes. Should the center's transformer model chosen to perform embeddings be somehow related to the LLM model used? Not necessarily. We can use a different, even big companies now like OpenAI and Google have their own embeddings model. I can create embeddings model with a different model, and I could even use traditional embeddings with where-to-vec. The embeddings is only the retrieval. It is only a search engine. We just search inside our text for the most relevant parts of the user's question. And then the model is very important, and the embeddings in order, of course, we need to have a strong embedding model in order to get good context. But also important is the LLM in order to have a process and some sort of understanding of the text, because usually the embedding prompts, the augmented prompts, are very big prompts. So we need a capable model there. But Regarding the point raised, we can use a very different model for embeddings and a very different for an LLM.